Hello, and welcome to this ASAP Next Generation presentation and software demonstration presented by Bro Research Organization. This demonstration describes the new features of Bro's ASAP Optical Engineering Virtual Prototyping and Simulation software. ASAP Next Generation, or ASAP NextGen, or NextGen for short, offers a novel paradigm in optical simulation software using entirely new manager and viewer-based interfaces coupled with parallel and distributed processing. Development of ASAP NextGen was done to support customer requirements, your requirements. You, our customers, require constant product improvement, and your two most frequently requested requirements are parallel processing and usability through easy-to-use user interfaces. We truly believe that ASAP NextGen meets these requirements and represents an innovative, fast, and intuitive simulation environment for novice ASAP users while preserving, improving, and expanding what is familiar to experienced ASAP users. The last point is an important point because we did everything we could to maintain a balance of familiarity for existing ASAP users while providing newer and easier to use tools for all ASAP users. ASAP NextGen's development comprised three major areas that are dependent on each other and hence three major work phases carried out simultaneously to meet your requirements. These were underlying architectural modernization, kernel parallelization, and of course the new user interfaces. You will not necessarily see the underlying architectural modernization, but it was absolutely necessary to parallelize the kernel and create new user interfaces. This development has been a major multi-year undertaking requiring rewriting the underlying software architecture, user interfaces, and parallelization of the computational kernel. We hope that you will find it was well worth the wait. Our goal today is to introduce you to ASAP's new interface, the managers used to improve your workflow efficiency and productivity, including the entirely new optics and workflow managers, and new and improved viewers integrated into the interface, as well as parallel processing. Let's get started discussing ASAP's new interface. ASAP NextGen's user interface is comprised of a main window, managers, and viewers. Managers are used for efficiently administering your workflow and include the optics, workflow, and script managers. You can use the catalog managers to efficiently and conveniently access and create optical property data, sources, and commercially available stock lenses. You can use the macro and $STR managers to efficiently create and modify macros, user-definable interface screens, and templates. And a new optimization manager is available for automated design. ASAP NextGen's interface is also comprised of a series of viewers for examining the results of your simulation. The new persistent 3D viewer is integrated into the optics manager and automatically updates your system geometry as you design. The CIE viewer is completely redesigned and taps directly into ASAP's kernel calculations of tristimulus values, chromaticity coordinates, and a variety of color spaces, as well as correlated color temperature. ASAP NextGen has an entirely new visual appearance viewer to see the visual appearance of converted CIE XYZ tristimulus values to a standard RGB or sRGB space. Bro has developed ASAP to be one of the most powerful commercially available virtual prototyping software simulation tools that can solve the widest class of optical engineering problems. For example, ASAP can model geometrical and physical or wave optics and simulate systems from the bulk to waveguide across the electromagnetic spectrum from the X-ray to the millimeter. And now ASAP NextGen combines that power with a variety of easy-to-use managers and viewers built into a general interface that allows efficient use of the software based upon your level of familiarity with optics, optical engineering, and ASAP's optical simulation paradigm. If for some reason you cannot solve your problem within the new easy-to-use interfaces, you can tap directly into the ASAP's powerful optical engineering specific programming language or choose from a variety of popular programming languages like C#, Visual Basic, and Python. And this is an important philosophical differentiation for Bro that has guided our development. Some optical software simulation companies may tell you their graphical user interfaces will allow you to do all of your simulations within the context of their graphic user interface. But the reality is, they most likely will not. Our Optics Manager's graphical user interface is powerful and will do many types of simulations, but not all, and that is why we have multiple interface tools. The best a graphical user interface can achieve is to offer a general tool for solving a general class of problems, that is, unless it is an application-specific program. However, most of your problems are application-specific, and they do require a specialized set of tools in order to solve the problem. Furthermore, the general user interface typically only gets you started before you are required to use a programming language to finish the problem, provided the software has the capability, flexibility, and power to solve the problem in the first place. ASAP has its own optical programming language and does not force you to learn yet another programming language to accomplish your tasks. After all, a product that cannot solve your problem is impossible to use by definition. Now, let's spend a few moments discussing the main window of ASAP's NextGen's interface. ASAP NextGen is composed of a main window from which other elements are found, including menu items, toolbars, and workspaces. The main window contains menu items and toolbars with icons that are configurable and customizable to your workflow. The workspace area is used to access the optics, workflow, and script managers, as well as tab control between the workspaces, ASAP examples, ASAP projects, and files. The workspace area contains tab controls for navigating NextGen's managers. The input area is used to examine your local and remote processes, command line input, text input. It also contains a system level status bar. The command line input allows you to input ASAP commands directly into the interface and kernel. The text output window displays all numerical results of ASAP's calculations. The status bar is a visual indication of important system level parameters, and the results area is used to display a variety of files, plots, and simulation results. The new main window is customizable with undockable and docking panels and tabs so that you can configure your workspace to your workflow requirements. The new toolbar of the main window is designed to be easy to use, navigate, and access ASAP's many features, new and old. As previously mentioned, the icon positioning is customizable and populated with useful icons for configuring a variety of program preferences. You can easily specify common system settings for your simulations in one convenient location. The main window toolbar also includes a custom toolbar for creating user-defined functionality with custom icons. Help is an important component of any product, and NextGen's new adaptive navigation help system provides viewing from help from desktop monitors to mobile devices and consists of an expandable table of contents and an index glossary with focused search capabilities. Each found entry displays a topic name, several words from the topic body content, and the full relative path of the topic. Search autocomplete is also now available, showing suggestions as you type into the search field. And the standard ASAP command line help has been completely, and I do mean completely, rewritten and updated. Before we discuss the optics and workflow managers, let us spend a few minutes introducing catalog managers because they are used for both the optics and workflow managers and many times are the starting point for simulations. Catalog managers are software tools designed for you to manage a variety of data commonly required for optical simulations. This data can include a variety of manufacturer and measured data for light sources, lenses, media, coatings, scatter models, functions, and variables to input data in any of ASAP NextGen's optics, workflow, or script managers. We literally could spend the entire presentation just discussing their features, but instead of exploring them in excruciating detail now, we will introduce several of them here and show you them during the software demonstration. An important catalog manager is the light source catalog, which contains a large number of manufacturers' sources with sophisticated geometry models and accurate emission properties. First, search for the light sources in the catalog, then create rays for existing ray sets. You can create rays for mono or polychromatic sources. Choose your source wavelengths, generate those rays, and then use existing rays to assign ray files to geometry, and then complete the source creation. The lenses catalog contains a wide selection of manufacturer stock lenses. You can search for stock lenses in the catalogs and use them, copy and modify the stock lenses and insert them in their model, or you can create singlet lenses from scratch by entering their optical prescription and inserting them into your model. The media catalog allows you to choose from or create a wide variety of refractive index materials. Choose refractive indices from the catalog, create refractive indices through media formula or dispersion formula, create refractive indices through table data. The coatings catalog allows you to choose from or create a wide variety of coating materials. Choose predefined coatings from the catalog, create coatings through prescriptive data, create coatings through tabular data, or create coatings through ASAP's digitizer. The scatter catalog allows you to choose predefined scatter models from your catalog and use them in your simulation, or you can fit scatter data to ASAP scatter models and use them in your simulation. The functions catalog allows you to choose predefined functions from the functions area or create functions in the catalog. And the variables catalog allows you to define variables to use throughout your ASAP simulation. Let's now spend a few moments talking about ASAP NextGen's new Optics Manager, and we'll follow that up with a demonstration in the software. If you are a new or infrequent user, NextGen's Optics Manager is designed to easily manage ASAP's four-step process of system, source, trace, and analysis. The Optics Manager is designed to be easy to use for a beginning or novice ASAP user with no prior ASAP experience and whose trip through the ASAP workflow initially requires management and/or direction. You use a CAD-like tree structure with uncomplicated and convenient input menus and catalogs for materials, lenses, and sources, while the integrated 3D persistent viewer automatically updates your system geometry as you design. Entire simulations can be performed within the Optics Manager without writing a line of script. But the Optics Manager also allows you to create a working script for you to access ASAP's powerful optical programming language for even more complicated simulations. When you're finished creating your simulation, simply run the simulation and view the results of the analysis. Let's examine the Optics Manager by simulating this TIR system with LED in the Optics Manager. We will see a variety of features that were presented up to this point. We will now switch over to ASAP for the actual software demonstration. We first start our system model by assigning system settings. There are a variety of different system settings that you can choose from. For the time being, we'll just set some parameters in wavelength and power and interpolation wavelengths. For right now, we'll change this from watts to lumens since we're going to be doing photometric analysis in this particular simulation. We'll then change set the interpolation wavelength sections, and we will set this using the auto generate wavelengths feature. We'll start at 0.4 microns and we'll go up to 0.75 microns, and we'll choose 29 interpolation wavelengths, and then we'll auto generate those wavelengths. We'll press OK. We will next generate some variables for our simulation. So we open up the variables area, the variables manager, click on variable name, and enter our first variable, which is related to the parabolic reflector, which will form part of the TIR lens, and we'll give that a value of 4.2. We'll then set in the base semi-diameter, which will be used in the simulation, 4.2, and we will define a base obscuration ratio of 0.8. We will apply those. Next, what we will do is basically outline the different geometry components that we're going to put into our model. We'll come over to the Geometry tab and insert a geometry branch. And the first branch we're going to put in here is going to be the TIR lens itself. Now the TIR lens is going to be composed of an inner component, so we'll insert another branch down here, and we'll call it inner lens. It will be comprised of a parabola, and it will be comprised of an outer lens. So we will insert another branch in there for that and call that outer lens. We'll also be inserting a detector later on, so we'll go ahead and put that in now as well, and we'll call this detector. Now we'll begin defining the actual geometry for these different components. Let's start with the inner lens. We're going to create a geometry component here, which is going to be the base. We'll create that out of a planar element. We'll call that base. We'll come down here and set its location at 0. It will have an elliptical aperture. And here we will use some of our variables which we previously defined. Base semi-diameter, diameter, and it'll have a central hole. When we're finished with this, we click Apply, and several things happened. First of all, the geometry is loaded into ASAP and appended to the CAD-like architectural tree structure in the Optics Manager. Simultaneously, the persistent 3D viewer is opened, and you can see that actual geometry which has been created in the persistent 3D viewer. Now, the next thing that we're going to do is add some optical properties to this component. So we'll come up to our media catalog, and we will select a media that's going to be on either side of this component, which will be air, and we're going to make this component out of a polycarbonate. So we can go into the media catalog under plastics and look under plastics, and we can see polycarbonate. We can choose this polycarbonate. Now, if you're interested, you can actually look at the dispersion formula for that. It's available. You can copy that formula, or if you wanted to, as we had showed previously, you can actually create your own dispersion formula. But for now, we're going to simply accept this polycarbonate as the default for this refractive index. We hit Apply, and we can see that a media is applied to that base component over there. Okay, now what we want to do is apply a coating to this as well to tell the ASAP how that light is going to refract or reflect off of that particular geometrical component. We come up to the coatings optical properties. We click on that. We're going to assume that this is a bare substrate. We have a wide variety of coatings that you can choose from, however. You can choose from coatings by a layer description, and we can just take a quick look at this. You can actually see the layer by layer prescription of that. You could actually create a simple coating if you wanted to of a tabular nature. You can choose coatings from inside of the catalog manager for coatings, or you can actually come down here and if you wanted to digitize data and use that particular data for your dispersion materials. We won't do that in this example, but just to show you that it can be done inside of ASAP. We're going to, again, accept the defaults, but down here we're going to assume that this is just transmitting only. We're not going to worry about any of the reflected component, which reflects off of that base segment. We'll press the Apply key, and that coating is applied to the inner lens. We can collapse this down and concentrate now on creating the sides of that inner component of the TIR lens. So we'll come up here and we will insert geometry. We will next insert geometry, and we will choose a tube for this side section of the TIR inner lens. We'll call that side, and we'll fill in the parameters. You can actually do mathematical equations inside of any of these fields if you want to, and we'll do that just to show that this can be done. And we want 4.2 times 0.8, and the semi-major width in the other direction will be 4.2 times 0.8 as well. Its location, the second location is going to be at 6, and the semi-major diameters here is going to be slightly tapered, so this will be 4.2 times 0.7, and this will be 4.2 times 0.7. And we verify that we have all of the components. We believe that they're correct, and we apply them, and what we should see is our tube, which is now part of the inner lens of our TIR lens assembly. We want to assign some optical properties to that side component as well. So we would come up to Media. In this case, we're going to assume that it again is made out of polycarbonate material. We'll apply that. We'll put a coating on here, and we'll assume that it is transmitting only as well for this demonstration. So now we have our side component, which is completed. What we need to do next is create a top component here, and of course the rest of the TIR lens. So we'll come in under Inner Lens, we'll insert Geometry, and in this case we're going to use a classical optical type element. We'll call this Top. Now its location is located specifically at this coordinate along the z-axis. It has a radius of curvature of 6. It is an elliptical aperture with semi-major diameters of 4 and 4. And we're specifically showing making this larger than what this outside diameter is, so we can show you how you can do some bounding of geometrical entities inside of the optics manager. We'll go ahead and apply that, and there's our surface right there. Now clearly this surface is on the outside of this element, and we'd like this element to trim this element right here, and we can do that. We come back over into the optics manager and we click under bounds, and we can see that we have a number of selections right here. So what we want to do is we want to trim the top lens with the side lens. So basically we're going to select the side lens and do a Boolean AND as a trimming function on that. And we're going to choose everything that's on the negative side of that surface normal and apply that, and there we have our trimmed surface. Now the 3D persistent viewer and the 3D viewer in general inside of ASAP has been significantly enhanced such that now you can actually look at transparent components within the 3D viewer to see how your geometry is actually fitting together. We now have to assign some optical properties to this top section. So we would do a media. We'll again assume it's polycarbonate. We'll come in and set a coating, and in this case we're going to set this to transmitting as well and apply that. So now we have our intersection component of our TIR reflector, which has been completed. Now let us concentrate on the actual parabolic reflector component of this TIR lens. We'll come under the branch of parabola, and we're going to insert geometry there. We're going to make this out of a traditional optical component. We're going to call this the reflector, and we're going to put its location at -2 in z. Now its radius of curvature is going to be that reflector curvature variable we previously set, and we're going to make it into a parabola by assigning a kind of constant of -1. It will be an elliptical aperture. Its semi-major width is going to be 12 by 12, and it's actually going to have a central obscuration hole to account for the base of this TIR reflector component, and that's going to be 0.35. So once we've verified that our components are correct, we click Apply, and we should see our parabola, which is now inside and part of the model. We can change this to a transparent mode so we can see all the components which are inside the model. Now we need to assign optical properties to our reflector. So we'll set a media, again assign it to be polycarbonate. Now we set the coating on this. We're going to set this to be reflect because we don't want to see any of the light which escapes out of the TIR for this particular simulation. So we'll apply that, and our reflector is now set up and ready for simulation. Now we have to concentrate on a much more complicated component of the system, and this is this arrayed pillow lens out here, and construct that and get it integrated into the geometry. So we'll come to our outer lens here, and we're going to insert some geometry, and we will call this, we'll create it out of another optical component, and we're going to call it the top of the outer lens. It's going to be at a Z location of 14.7064. It'll have a radius of curvature of 12, and it's going to be a parabolic component as well. Now its elliptical size is going to be different. It's going to be 2 by 2 because its size is the size of each of the individual components, which will go across and make up the pillow lens. There will be no central hole obscuration, and we will go ahead and apply this into our model. We need to change the aperture from ellipse to rectangular, and there we have it. Now, in order to get this pillow lens to work correctly, we're going to have to move this component over here so that when it's replicated, it's centered on the main component itself. Before we do that, let's go ahead and get our media assigned to this very quickly, since it's easy to do, since ASAP has remembered many of these different components. So we transmit. And now let's go ahead and get this positioned correctly. And this is going to be a relative shift, and we're going to have basically 6 by 6 elements, or 7 depending upon whether you use the original component itself. So we'll move this component into space where it's supposed to be, so when it's replicated, it will be replicated across the face of our geometry, and there it is right there. And now we'll come in and we'll actually do the replication of this. There is an array command built into the Optics Manager and actually inside of the ASAP kernel. So we'll set this up to the number of components we want. And then we'll set the shift that we want along these axes, the x-axis and the y-axis. And then we will apply that. And there is our array component. We could continue the simulation like this, but what we'd really like to do is clip that arrayed component with the parabola. So we can do that. We can come down to our outer lens top component. We can come to bounds, and you can see there's a number of other components in here now. So we're going to turn this off, select none on this, and we want this top element, the outer lens top, to be basically trimmed by this parabolic reflector. So we will do a Boolean AND on that, and we want to take everything which is on the positive side of that. We will apply that. And now we have our outer lens, which is properly clipped by the parabolic reflector. We're not quite done, because what we'd like to do now is have the parabolic reflector actually trimmed by the lens itself. So we will go back to the parabolic reflector. We will choose the bounds command again, and we'll turn off these other parameters. And what we now want is we want the parabolic reflector basically trimmed by the TIR lens outer portion. So we will do a Boolean OR on this, and we will select the negative side of those components and hit apply. And there we have it. We have our TIR lens, which is now has been completely set up and properly trimmed by various geometrical components within the model. We're not quite finished with creating the geometry. What we want to do now is create a detector plane, and we'll just set this and call it a plane. That's going to be at a Z location of 200 away from the global origin of the system. We'll set this to be 100 by 100 for the semi-diameters of that detector plane. We don't need a central obscuration, and we will apply that, and we should see our detector plane in with the model, and there we have it. Now we can of course isolate and look at different components inside of the 3D viewer, but each time that we update this or refresh the 3D viewer, basically what happens is we're put back into the mode of looking at all the objects. And of course, these objects down here are different colors, and what we like to do is set their attributes such that they're the same colors and help us better identify the different components within inside the model. And we can do that. For example, we can come down to the TIR lens, click on the inner lens here, go to the attributes, and we can set that to a color of, say, goldenrod. So the inner components now are set to that goldenrod color. We can come down to the parabolic reflector, and we can set that color as well. And let's set that color to a color of blue. It's consistent with what's in our presentation. So that's blue, and then we come down to the outer lens up here, and we can set the outer lens color, and let's set that to be red. And there's our red color. Now we still have this detector plane sitting out here, and we have a special attribute feature, which just in the 3D viewer, we can come down and we can set the attribute onto this to a hidden color. And what this does is it tells the 3D viewer to basically just ignore that component for visualization purposes so we can concentrate on the geometry which is down here. And the other thing I want to note is on this you can actually apply these attributes and any of the optical properties either at the parent level of the branch that you've set up or at individual levels. So this gives you full and complete control over all the geometry modeling which is in your system model. Now at this point it's a good time to basically save your work in case there is a problem. So we're going to go ahead and we're going to save this, and we're going to save this as TIR lens array, and we'll call it demo. Takes a few moments to save all of the database information, but this is just in case in the unfortunate situation where something happens and your computer crashes, a power outage, or what have you. It's always good to frequently save your data. We've got the system geometry basically set up. What we need to do now is we need to add a source into this. And we will do that by accessing the sources in our light source catalog. So we'll click on this, and we will come down to LED sources. You should note that there's a variety of different sources in the catalog. There's arc sources, there's cold cathode fluorescent tubes, there's filament sources of a wide variety of types and manufacturers, and of course there's a wide variety of different LED sources that you can choose from. We're going to choose a luminous LED, which has a basic correlated color temperature of about 6,500 degrees Kelvin. So we will click on that, and we want to insert that into our model, so we'll click on the insert button down here. This brings up the light source wizard, which is part of the catalog, and it has a number of different features. You can create new ray sets, and this is very useful and convenient if you want to create a small set of rays to do simple analyses, to set your geometry and your models and get them configured before you do a very large ray trace to do a simulation. Or you can actually use existing ray sets if in fact they actually are in your system on your disk already. So we're going to create new ray sets in this particular example. So we click the next key. We have the ability of doing this at a single wavelength. We don't want to do that. We want to do this at multiple wavelengths. And the total ray count we're going to set to 1 million for this particular example. So we'll hit the next button, and we're presented with our spectrum screen. We do want our rays to go from, or our sources to the bandwidth of the sources to range from 400 to 750 nanometers. But we want it to be consistent with the number of interpolation wavelengths that we created. So we will set that to be 29 and click the add button. And those sources are set over here. You can set your own wavelengths. You can create them at specific intervals. You can click on this graph over here, do whatever is necessary in order to create your particular bandwidths for your sources. We'll click the finish button. And now what ASAP is doing is it's going off. You can see this in the background here. It's beginning to set up those sources. for your simulations. And this is going to take a few moments. Now, when this is complete, you can go out and you can select your ray sets. And here's the ray sets which were created. And we will select these ray sets. And hit OK. Open them. We're going to shift this ray set slightly because we don't want its geometry to interfere with the actual geometry of the TIR lens. So we're going to shift it back by about 3/4 of a millimeter. Press the close button, and then ASAP again will go out and add that geometry and that source into our model. And you can see it has also appeared over into the tree now. With any ASAP analysis or any analysis in general, it's always good to verify that what you have created is in fact going to be what you want to simulate. And we have a special area within the Optics Manager, which is called Source Analysis, which allows us to basically analyze the source before we actually trace any rays. And that's what we want to do here. So we're going to do a couple of things here. We're going to look at some of the source components radiometrically and photometrically. So first, radiometrically, we're just going to do what's called a statistics all or a stats all under source analysis. And what that will tell us is basically the total number of rays and the total amount of radiometric power in the source. Now what we'd like to do is actually find out how many total lumens are in this. There is, of course, a lumen count which is set, but we want to verify that that is correct for this source model. So we will come over to here into our source analysis area, and we have a variety of photometric, radiometric calculations that we can do. We're first going to do a luminous intensity calculation in direction cosine space, and all we're doing that for is to calculate what the total amount of lumens is in this particular source. So we will click on this, and it presents us with the screen for which we have to fill out the data. And we're going to change some of the settings here. We're going to, since the source doesn't emit completely into the full hemisphere, we're going to set those direction cosine limits down slightly. The horizontal axis we need to change to X, and we need to update its minimum and maximum extents of its emission axes. We'll take the rest of the defaults down here. We can change the standard observer model or the wavelength resolution for the photometric and colorimetric calculations, but we'll go ahead and accept these defaults for resolution down here and hit the apply key. Once we've done that, we want to come over and actually do a chromaticity analysis on this. And we click the chromaticity analysis, and you have a wide variety of different choices to choose from for the different components that you're initially going to look at in any particular viewer window. The tristimulus Y is what's used to calculate the photometric components, so we're going to go ahead and choose that. And then we're going to do a isometric plot of that distribution just so we can see what it looks like. And then we'll hit the apply key there. This calculation was done in direction cosine space, which is one space in which you can do luminous intensity calculations. We'd also like to show you what this calculation looks like in an angle space coordinate system. So we will go back to our source analysis here, and we'll look at our luminous intensity options for doing the luminous intensity in an angle space coordinate system. We'll click on that, and we'll have to change some of our parameters here to make sure that our computational coordinate axes are consistent with the emission of our models and so forth. The subdivisions for this calculations we're going to set to 90 subdivisions, so it's going to be basically at every 2-degree intervals. This we're going to set to 180. So by setting these two zenith and azimuth angles, we're going to look at the hemisphere of radiation of the intensity pattern coming out of that particular source, and we're going to set this to 90 as well. We will maintain the same resolution values down here, and we will hit the apply key for that, making sure that we have our parameters correct, and that is added into our simulation tree. Once we do this, of course, we want to come back and do a chromaticity analysis on this. In particular, we're interested in the Y tristimulus value, so we will go ahead and choose that for our initial viewing of our chromaticity analysis. And then we'll look at an isometric plot of that again, just to see what it looks like. And then we will actually look at and perform a full CIE calculation on that, looking at the components of that calculation on a CIE graph so that we can see where it stands on the familiar shark fin diagram. Now, ASAP also has a new feature which has been added into ASAP NextGen, and this is the ability to do a visual appearance. So we will click the visual appearance button down here and add that into our simulation tree so that we can see what this source looks like in terms of an angle space before we actually do the calculation or do any further ray tracing and trace analysis. Again, it's a very good idea to basically save your system geometry and your analysis up to this point. And that's what we'll do right now. Then the next thing we're going to do is we're going to run this simulation inside of ASAP to verify that the source is actually what we think it is. It's in the correct position and it's doing what we want it to do. And to do that, it's always a good idea to come over and refresh the kernel by restarting ASAP. And then we come over to the workspace area for the Optics Manager, and we press the Run the Optics Manager key, and that will actually execute this particular set of requested simulations inside of ASAP. And you can see them being performed down here. This again will take a few moments for this to run, but now we can see the results of our particular source. So first of all, we'll go back up and look at this calculation that we did for the radiometric components. The stats position and stats direction tells us what the flux is for this purely in terms of radiometry, and it gives us statistical information on the spread of the rays, both in a positional sense and a direction cosine sense. And then we did our calculation of the luminous intensity and direction cosine space, and right now this particular source is set to emit about 303 lumens. And we can see over here, this is basically the output of that particular source in angle space, and this is the output in direction cosine space. This is the CIE graph of this, and each one of these components on here is basically a different component of the pixel that was used for the calculation of this luminous intensity calculation in angle space. And this final plot right here is a plot of what the visual appearance of this would look like, and you can actually scan through this plot and look and see what the candela amount is for this particular source. If you're interested, there's a number of features where you can tile components within the interface, so you can see all these components together and see what they look like, depending upon your workflow desires and your preferences for viewing the abundant amount of simulations which can be done inside of ASAP. Now we're ready to continue our ASAP simulation, and the next part of the four-step process is to do the actual ray trace. So we come over to the trace item in the Workspace Optics Manager tree. We do want to see some of the rays which are plotted in this particular simulation, so you can see what this looks like. So we'll check that box. We'll change the plot title here to say System Ray Trace. We don't want to see all the rays traced because remember there's about 1 million rays which we've created. So we really only want to look at, let's say every 10,000th ray which is traced. We do want to plot the geometry. Otherwise we would just see the rays being traced with none of the geometry. Could be an interesting picture, but the geometry would not be there. And you have a number of other options down here. We'll accept the auto scaling for the window, and then we will go ahead and insert this into our tree, and our ray trace is ready to go. Now at this point, if we ran this file again like we did before, what you would see is basically just the simulation, and we would see the results up to and including the ray trace. Now once we have done the ray trace, we actually want to do some analysis. And one of the first and most important things that we do when we start doing an analysis in ASAP is we consider the object of interest where the rays are located. And in this case, that's going to be the detector plane. So you have the ability to choose whatever objects you want for your analysis, but we're going to just choose the detector plane, isolate the rays on that detector plane, and then we're going to look at basically an irradiance or an illuminance and irradiance calculations on that detector plane. So we'll apply this and put it into our tree right here. Now, as we did before, we'll first do an irradiance calculation just to see what the radiometric properties of this are. So we will click on the irradiance button under the radiometric calculations. We're not going to auto scale. We're going to specifically set the window sizes here to be about 75 by 75 millimeters. We need to change our horizontal direction, 75 by 75. We'll accept these resolution values and we'll hit the apply key. Now this will create a radiance calculation inside of ASAP. Now what we really want to do is we want to create a couple of things. We want to create a contour plot of that irradiance and a mesh of that isometric pattern and actually put it into the 3D file with this so we can see what the irradiance pattern looks like when we have done this calculation. So what we'll want to do next in terms of irradiance here is we're going to create a contour plot, and we can call this irradiance contour. We'll accept the defaults, but you'll note down here we can check this box and write that out to the 3D vector file. And if we hit apply on that, that is added into our tree over here. And we have another option over here, which is called the mesh option. And it will also allow us to put a 3D representation of the distribution data file, which is the results of this irradiance calculation, into our 3D vector file by clicking that box right there. So we will apply that. Now we want to finish our analysis here by performing some photometric and colorimetric simulations on the results. So we will come down to our photometric and colorimetric options. We're going to do an illuminance. So we'll click on illuminance here, and we're going to have to change some of the parameters here to make sure they're consistent with coordinate system and the size of the distribution at the detector plane. We'll accept those defaults. We'll click the apply key, and now we have an actual luminance calculation. And these are two different calculations. An irradiance is a calculation which is done with radiometric power, and a luminance calculation is a calculation which is done with luminous power. So now what we'd like to do is, again, on this luminance command, we want to do a chromaticity analysis, look at the tri-stimulus Y value because that will give us the photometric components of that illuminance calculation. We'll hit the apply key there. We'd like to look at an isometric plot of this to see what this looks like. We'll hit the apply key there. And then we'll finish this off with a CIE graph of the results and a visual appearance. Before we get started, let's clear out these previous files from our source distribution. Let's go ahead and restart and refresh the kernel inside of ASAP. Again, always good practice to just save your files. So let's go ahead and save those files. Give this a few moments to save. And then when we're ready, we will click the Run the Optics Manager file, and let's see what the results look like. Again, it'll take a few moments to set up the rays for the ray trace, and then it will take some time to do the ray trace. But one of the new features in ASAP NextGen is that we have parallel processing. And in this particular case, this computer is being parallel processed with a 2-core machine. So I'm using 2 physical cores to actually make this calculation. So that makes it about twice as fast as it would be with a single core in an ASAP simulation. You can see the rays tracing on the screen over here to the detector plane, and you can see the basic timing that it's taking to do the ray trace down in that window. It's done. Now we're doing the actual simulations of the irradiance at the detector plane, and there we have it. So if we come back and we look at our chart right here, again, here's the initial source verification. That is the irradiance contour which is put into the 3D vector file, and that's the isometric plot of the radiation pattern at the detector plane. This is the chromaticity results of the source. This is the visual appearance of the source, the actual ray trace itself. We can delete this vector file because its components are copied in here, but you can see the contour plot, which is on the screen, and you can also see the mesh plot of the irradiance pattern of our TIR reflector and source. This is the actual chromaticity diagram of that. You do have the ability to set different things in this space. For example, you can look at different gamut areas. You can actually come down here and set the different light points to see where they're at on this diagram. This is the results of whatever tristimulus component that you have chosen, and you actually have the numeric results down here that you can look at as well, up to and including correlated color temperatures for each of the pixel locations within the computation. And then the final plot is the actual visual appearance, or what this would look like, what the illuminance would look like to the human eye for this particular ASAP simulation. Once you've completed your analysis in the Optics Manager, you can click on the Generate INR Document button, and that will create an output file of the ASAP INR script of the entire analysis that you've just done, including the system geometry. You could actually take this file if you wanted to and run it on its own, or you can modify it or change it and perform even more complicated analysis that, for example, you might not be able to do within the Optics Manager itself. Let's now return to our presentation and discuss how IGES translation is handled in ASAP Next Generation. IGES translation with optical property assignment to your geometry is handled through the Optics Manager, or you can directly translate IGES files into an INR file for further processing. It's probably best to examine this through software demonstration so that you can see how this process actually works. So return over to ASAP. I'm going to clean up the results of our previous analysis since we're done now. And we'll get rid of all of this input information, delete the current Optics Manager program, and clear all the components inside of this. We will come up to the Geometry button, right mouse click on this, and you'll see that you have an Import CAD File capability. There's also a CAD Import File button up here. In addition to that, there's also the ability to import files from other optical design programs. If we right mouse click on the Geometry button and hit the Import CAD File, we have a CAD file which is already available. We're going to go ahead and choose that file, and once we choose that file and press the Open button, you're presented with the preferences screen for the CAD import. Now, it's important to note that there are actually two different translators inside of ASAP NextGen. One is controlled primarily by these components on this side of the preferences screen, and one is controlled by these components on this side of the screen. This translator is an ASAP written IGES translator, and this translator, which has the words geometry conditioner on it, is actually a third-party translation program. We will use initially the ASAP IGES translator to demonstrate the IGES translation inside of NextGen. We'll accept these defaults that you see right here, press the OK button, and what happens is the ASAP NextGen goes out and it basically translates the geometry, and in doing so it's actually going to pop open a 3D vector file for us as well. And this is a fairly large IGES file, so we will give it a few moments to plot the faceting of all the geometry within this file. And there it is. This is basically a simple type of headlamp for automotive application. You can see the components which are basically in the 3D viewer, and they have come in at various levels within the IGES translation within the Optics Manager over here. If we wanted to, we could come in and we could look at these different components. For example, this is trim surface 53, and we can isolate that trim surface over here as well, which is right down there. You have the ability, if you want to come in for the reflector, for example. If you wanted to apply a coating to all of that at that parent level, you could do this, and let's say that this is going to be an idealized coating of a reflecting component, just perfectly reflecting surface. We click on that and apply it. So now that coating is going to be applied to all the components within this element here. Alternatively, you could come down if you wanted to and isolate each one of these components individually, and you can apply optical properties to them if you so choose to do so. And of course, when you are done, you have this, you could save this file in the Optics Manager if you wanted to, but you can also, if you wanted to, output this into an INR file. And here's the results of that calculation and that translation. And if you wanted to, you can do the same with CAD import from this button up here. It will run you through the same preferences screen. You can say OK. But this now is directly output into a INR file where you would then have to go in and assign whatever optical properties that you wanted to, or modify this file as you wanted to or see fit, because it is not loaded into the Optics Manager for easy and convenient control of the assigning optical properties to the various geometrical components of your I just translated model. Let's now return to the presentation, and let's spend a few moments talking about ASAP's new Workflow Manager. NextGen's Workflow Manager is designed to provide you with a more convenient, quicker, and easier approach to scripting. The Workflow Manager is designed for an intermediate or advanced ASAP user who has familiarity with the ASAP scripting and macro languages, but may require assistance in structuring ASAP script files and command syntax. The Workflow Manager has been painstakingly laid out to follow the ASAP workflow from the top to the bottom and from the left to the right. And the expandable tree structure leads you through the ASAP process with commands laid out in appropriate order for use. All ASAP commands are included in the Workflow Manager, including all of the macro commands. You can use the detailed workflow tree structure or search field to locate the command or macro you need for your script and simply fill in the relevant command parameters in the workflow grid fields. Required entries are color-coded. The Workflow Manager can be used on any INR file, one that you create from scratch, or even one created from the Optics Manager. The workflow goes from top to bottom, from left to right. There is help syntax, which matches the commands which you have chosen within the workflow tree, and required entries are color-coded. So if you attempt to enter an ASAP command and you haven't filled in the required entries, then you will be flagged to say that by the program that you need to enter in the appropriate value. Options are accessed through a variety of drop-down menus within the workflow grid. If a required entry is not made, you are prompted with a warning, and it's up to you to choose how you want to deal with that particular situation. You can insert the commands at the cursor location in the script, the command bar, the clipboard, or run the command. Context-sensitive help topics show the exact detail you need to assign associated command parameters. You can create an INR directly from the Workflow Manager, or first create a script file in the Optics Manager for further elaboration within the Workflow Manager. And of course, there's an undo button for mistakes. There are appropriate modifiers listed with each command, so as you bring a particular command up into the workflow grid, you'll see only those modifiers which can be used with that particular command. There are bookmarks available, so you can bookmark various places within your INR file for quickly accessing those points during your ASAP simulations. And you can turn on or off the Workflow Manager with the Workflow Manager button. Let's briefly examine this in operation in the INR file that we had translated over through the iJust translator. Here's a basic INR file. We can come down to the bottom of this, and perhaps we wanted to put in with the Workflow Manager, which is we would access through the Workflow Manager tab. Perhaps we wanted to put in a detector plane. We would come up here to create the system model. We can go to Object Definition or System Geometry. We have the ability to put in the branch command if we wanted to, or we could go directly into and begin creating a variety of different ASAP entities. In this case, we'll create a surface, just to demonstrate this again in the Workflow Manager. Surface is a keyword. We click on that. You can fill in whatever parameters that are required. You hit the Insert key, and that is inserted into that area into the INR file. Now if we wanted to insert a simple plane to act as a detector, we click on plane and you can see here are the components for the plane. And the plane command actually has a wide variety of different options for inserting a plane. It can be a simple plane orthogonal to a component, or it can be normal to a component by entering in the normal direction, or you can actually put in a point planes command where you put in 3 points to define the plane. We'll check this particular plane command. We'll set it at a location of, say, 100, just for this particular example. We'll set the semi-width at 100, and then as we come down here, we hit the insert key, and it's inserted into your file. And again, note over here that any of the modifiers which are appropriate for that particular command are brought up into this area, into the workflow grid. All of the commands in ASAP are in the workflow manager, including all of the macro commands. And in fact, you can actually create your own user-defined macro through this macro template if you wanted to within the workflow manager. Let's spend some time now talking about ASAP script, macro, and $SCR managers. The freeform or script manager has been designed and enhanced for the advanced user who has an extensive knowledge of ASAP and is able to freely program INR scripts for a wide variety of applications. The script manager is designed to allow for direct entry of ASAP commands into an INR file using the ASAP editor. The script manager is essentially the existing command input interface in the current version of ASAP with an advanced editor. The script manager has streamlined file control for accessing a variety of text files, including INR files, and you can set a variety of editor preferences to customize your workflow environment. Command tips can be turned on or off, and if on, will launch help by clicking the command reference. The macro manager is especially useful for managing workflow with a large number of macros. You can individually display and modify macros within the context of a much larger, complicated file. This allows you to concentrate on the task at hand, that would be a specific macro, without being distracted by the other components in the INR file. The workflow manager can be used in conjunction with the macro manager for efficient creation of user-defined macros for your application-specific work. Let's examine this feature through software demonstration. We return to our ASAP example that we set up before, and we will clean things up. We'll get rid of the Optics Manager and the translated files and refresh and restart ASAP. And we'll bring in a predefined file which has some macros in it just so you can see how the macro manager works. We open this file up. This is an example of a triplet inside of ASAP. It's a very simple triplet example. And it has a series of macros down here. If you click on the Macro Manager button, you can see that you're presented with a list of any of the macros which are in your ASAP INR file. And of course, you can come in here and you can add in whatever commands that you would like to. The ASAP Workflow Manager also works within this context. So if you wanted to come in and do some of these system settings and so forth as well, you can actually use them and put them in here if you wanted to. For example, if we wanted to put in the show command, here it is. We can come down here and just insert this in, and it is part of the file right now. So if we were to run this file, there is our ASAP simulation and the two show commands which are actually inside of the and part of the simulation. Closely related to the macro manager is ASAP NextGen Screen Manager. It allows you to create custom input screens for inputting data into ASAP for a variety of applications. Let's examine this feature through software demonstration. What you see on the screen now is an INR file composed of several macros, and these macros are set up and created to create a simple mirror inside of ASAP. Let me demonstrate this by running the file. I click on the Run button. I'm presented with the user-defined screen, which is the mirror input menu. We can then begin to input data into this menu, which of course is user-defined. And when we are finished, we press the OK key, and the mirror is created for us. Now, you might ask, how did you create that particular screen? Well, that was done through ASAP NextGen's $SCR Screen Manager. And if we click on that button, we see the actual input which was created to create that user-defined screen. You have the ability to create a screen in terms of text input, literal input, integer, floating point, and exponential number input, as well as putting in checkboxes for doing a variety of more complicated programming. Let's say that I wanted to add a box or an input into this. I could drag the text field down and then edit that text field and simply say this is a dummy field. I can, of course, increase the size of this box if I wanted to slightly and adjust it to whatever my needs are. Perhaps I wanted to enter in a particular literal or a number into that box. Let me drag a number over. So this is just a value which I can put in. This is the $SCR Manager input for easily creating files for ASAP screens. Down at the bottom of this is the actual file input that ASAP sees. You can see this input and what it looks like inside of ASAP by pushing the changes from the designer to the editor. So now what we see down here is this dummy field is put in here and my integer values are actually put in there. Then I can actually update the main editor with these changes. So now when I refresh ASAP and I run this file again, what I see is my dummy field down here. So I can type in my parameters, which I had done before. Make this into a parabola, give it 100% reflectivity, and I'll put in an integer value of 5 down there, press OK, and there's my geometry again. However, what's important is now that information has been put into a variable inside of ASAP, which you can now use for further ASAP simulations and analyses. ASAP also has a template manager for exporting and importing virtually any ASAP script. The template manager even has a direct link to ASAP system settings. The macro, screen, and template managers, along with ASAP scripting and macro language, provide an excellent application programming interface, or API, for custom applications and features not found in any other optical engineering simulation program. In fact, many companies use ASAP in the same way that we have designed the optics manager. They build their own custom interfaces using ASAP as the computational kernel. Let's now spend a few moments talking about the new optimization manager in ASAP NextGen. In previous ASAP versions, optimization was accessed through a bolt-on process or through the $iter command. Optimization is now integrated into the main user interface through its own manager. Its workflow is designed around a simple 4-step process: defining design variables, defining design objectives, or what is known as the merit function, defining objective constraints including penalty functions, defining exit criteria, and then running the optimization. It's important to note that any optimization file must run to completion prior to using it in the optimization manager. Let's design a lens to demonstrate the optimization manager and its workflow. The lens design will consist of bending the lens and adjusting the front conic constant of the lens. The focal position is the paraxial focal position of the lens. The lens was first laid out in the optics manager and transferred to an INR file. Let's begin by first cleaning up the previous ASAP session and restarting the ASAP kernel, and then first examining the lens design file which was created in the optics manager. You can see this is what the actual lens looks like. We did define some variables in this particular example, which are listed over here, and that file and all of its output was actually put into another INR file, which was called lensdesign.inr, which is shown over here. And you can clearly see what we have is basically a series of variables which define the components within our system file, and then a definition of the singlet, and then a ray trace down here in which we actually will use the RMS spot size as our merit function. So let me go ahead and run this file so you can see what its results look like. And I'll close down the optics viewer over here and go ahead and run this. So here's the initial lens, and you can see that the lens is not designed. The on-axis beam does not come to focus over here. In order to perform optimization inside of ASAP, we now launch the Optimization Manager, and we're presented with the Optimization Manager screen. We can give it the optimization study a title if we want to. We call this Lens Design Demo. We have a variety of different optimization methods to choose from, including Brent's, downhill simplex, and simulated annealing. The four-step process for designing a system inside of ASAP is listed below here, and we first start by adding rows into our design variables. We'll choose from a drop-down list of our design variables, and we'll choose K1, which is the conic constant of the first surface, and we'll keep that alias. Its nominal value is 0. We'll allow a minimum value from -3 to a maximum value of 1. And then we'll add another row into this, and we will add in the bending factor. We'll keep the alias the same. We'll allow this to go from -3 to 3. We'll keep the rest of the default parameters for the design variables in this part of the optimization process. We'll now design our design objectives. We'll add a row into this, and we'll search the list, and what we're looking for is RMS. It's an RMS spot size. That is the design objective for merit function that we'll be using. The objective constraints, we won't use any of those, and the exit criteria we'll set as about 50 iterations. You can also set acceptance criteria based on acceptance limits, relative divergence of the trial solutions, or acceptable noise limits as well. Before we run this optimization example and look at the results, what we want to do is come in here and comment out the actual trace plots that we're doing, because we don't want to see those when we're doing the optimization study. It would just take an additional amount of time to do that, and we don't need to see them. We'll look at the results after we've done the optimization. In order to perform the optimization, we hit the Start Optimization button, and as you can see, ASAP is now going off into the background, doing its various ray tracing, and you see a plot which comes up which shows what the graphical results of the figure of merit of the merit function looks like versus the number of trial solutions. So ASAP has reached the optimization, the number of trials limit that we've specified. We click OK, and now if we want to, we can see up here that the original variables, well, K1 was equal to 0 and X is equal to 0. We can save the system under evaluation, which simply puts those variables into the file. We can come back down here, and we will comment out and comment in the plot facets and trace again. We'll refresh ASAP, close the optimization manager, and run the INR file again, and we can see the results of our optimization. So over here, if we tile these plots, you can see the optimization before and after, and this is just a 3D representation of the optimization of the lens before and after optimization inside of ASAP. We can do this optimization not only on lens systems, but we can actually do them on a wide variety of systems, including illumination and/or imaging components, and that's what we'll demonstrate next. We have another file in here which is an illumination file, and we'll open that up. And the illumination in this file is set up a little bit differently. The optimization and analysis are set up in two different macros. And so we'll go ahead and run this analysis macro first so you can see what this actual optical system looks like. It's a reflector which is composed of variables which have a location, radius of curvature, and a conic constant of this particular reflector. So let's go ahead and run this file to see what this looks like. So it basically is an elliptical reflector with an extended source, and what we'd really like to do in this particular example is we'd like to optimize and maximize the amount of energy which gets to this particular detector plane over here. And that will require changing the position of the source and then changing the radius of curvature and the conic constant of this particular element. We'll go ahead and leave those in there. We'll come back down here, and the variables we're going to use are these variables here. And the merit function that we're going to use is basically the inverse of the power which gets to the detector plane. The more power that gets to the detector plane, the closer our merit function becomes to 0, and the closer to an optimum solution that we will actually have. We'll go ahead and refresh ASAP before we do anything else. I've changed this into the optimum macro, so that will run. We'll launch the optimization manager. Now, instead of putting all these variables in again, what I will do is just go out and grab an optimization study that we already have, which already has these parameters filled in. And here they are right here. And so there's our design variables. So the location of the source, the conic constant, the radius of curvature of the reflector, given its nominal values, its minimum and maximum values. Our design objective is the inverse power. We won't have any objective constraints. And our exit criteria, we're going to do 100 trial solutions, but we're also going to use acceptable noise limit. If from iteration to iteration the noise doesn't change by a particular amount, then we'll tell ASAP to stop the optimization. So we'll go ahead and then we'll start the optimization, and let's examine what happens. This will take a few moments for this to run. But you can see ASAP is changing various variables. You can see the numerical changes down here in this table, as well as the graphical results of the optimization. Give this a few more moments to finish. And it has reached the noise criteria, so we'll click OK. We're going to want to examine what this looks like, so we will switch this back to the analysis macro. We'll come up to here, and you'll note what the parameters are for the variables. We will save the system under evaluation. You can see that those have changed. So we'll then go ahead and close the optimization manager, restart ASAP, and then run this file, and let's see what ASAP did for optimization. Now we can see what the optimization looks like. This is the optimization ray trace. So this is the before the optimization, and this is the optimization afterwards. You can see that the system has been quite nicely optimized. Let's now spend a few moments talking about the variety of viewers which are available inside of ASAP NextGen. ASAP NextGen has a variety of new and improved visualization tools for examining a wide variety of simulation results. The more commonly used viewers are again summarized here. You've already seen some of these in the software demonstrations. ASAP NextGen has an improved and now persistent 3D viewer when used with the Optics Manager. The 3D viewer in general has many new and improved visualization properties, including a transparency mode. CIE automated photometry and colorimetry simulations as a function of illuminance, luminous intensity, and luminance previously were added to the computational kernel. This included automatic polychromatic source creation with sources based upon black bodies, CIE illuminance, user appetization functions, and tables. Kernel-embedded simulations or kernel-embedded photometric simulations of illuminance, luminous intensity, luminance, and kernel-embedded colorimetry analysis in the following color spaces: CIE 1931 XYZ, CIE 1960 UVW, CIE 1964 U star V star W star, CIE 1976 L star A star B star, and CIE 1976 L star U star V star. The completely designed CIE viewer is used to visualize these results by tapping directly into ASAP's kernel calculations of tristimulus values, chromaticity coordinates in a variety of color spaces, as well as correlated color temperature. Photometric and colorimetric results are now easily and conveniently displayed in the viewer in terms of graphical and numerical representations of the color space, and the results in the ability to independently graphically view any of the photometric or colorimetric analyses. ASAP NextGen has an entirely new visual appearance viewer to examine the appearance of converted CIE XYZ tristimulus values to a standard RGB or sRGB space so that you can visualize the results of your analyses. Let's examine these new visualization features through software demonstration. We again return to ASAP and let us clean up our previous optimization results. Reset and clear out the Optics Manager, refresh and restart ASAP, and then we'll open up a specific file, a CIE demo for visual appearance and chromaticity. This file is actually available through our online help, but it serves as a very nice example for examining the various viewers inside of ASAP. So let's go ahead and run this example and let's examine the results. The first thing we see here is the results of the plot of the geometry in the ASAP 3D viewer. And as you've already noticed or noted, you have the ability to put this into transparent mode and smooth shaded mode, as well as wireframe and other modes as well. What we have here is a system where we're going to create a very simple source, set it to a certain color temperature, and then send it through a 3-color filter system so that you can see the results. So the first results that you see right here are of the source, which is set to D65 or daylight temperature, and all of the points are matched on the same point on the CIE chromaticity diagram. The rays are being traced right now. They're being traced through the filter and these different various components of the filter, and these are the results that we get. So again, we have light which is being traced through this filter system. This is the source of light in the visual appearance viewer, which is going through first. We can see the values of the illuminance for this, and this is a visual appearance of that rectangular source. This is the CIE results of the source itself, and these are the photometric values of that. And you can see again, the data is available in a numeric or a graphical format for you to view and analyze. This is the results of the light, the source being traced through the filters. And so you can see the red, green, and blue components, and then just a neutral density component over here. This is a CIE diagram of that same plot. And you can see the individual components of the filter over here in that RGB space. I would now like to spend a few moments talking about ASAP's new parallel and distributed processing. ASAP was the first commercially available optical engineering software that had distributed processing, which is called ASAP Remote, and came out about 2001. And now ASAP combines that computational power with parallel processing. ASAP's remote or distributed processing allows you to distribute design and analysis tasks such as large ray traces, sensitivity and tolerance analysis, or to perform true Monte Carlo simulations over a large number of machines, thereby substantially decreasing the simulation time and increasing the user's productivity. Remote allows a properly licensed single user to access up to 100 CPUs or cores or more across multiple computers on the local area network, LAN, including the user's own PC. Remote processes can be distributed across a variety of single and multi-core PCs, as ASAP can automatically determine the number of cores available on each individual machine. Remote is real, extensible distributed processing, a first in the ray tracing software industry. Remote is fast. Below is a simulation of an integrating sphere distributed over multiple computers. And now, ASAP is going to get even faster through true parallelization of its computational engine. Parallel processing in ASAP is implemented through the Message Passing Interface, or MPI. MPI has been around for decades and used on parallel supercomputers for solving significant scientific and engineering problems using computers with literally thousands of available CPUs. MPI achieves this through the process level, which is very efficient, giving ASAP's kernel architecture. ASAP is now truly parallelized and distributed over multiple computers, which we believe to be an industry first and which no other competitor can duplicate if their processes are limited to multi-threading. NextGen's parallel processing works most efficiently on individual physical cores. Cores 0 and 1 are normally reserved for the operating system and ASAP on the host machine, and you are free to use as many other available cores on that machine for your simulations. We do not limit the number of cores you can use on a machine. But now, how fast is parallel processing on ASAP? Parallel processing, not including distributed processing. To assess NextGen speed, we compare its performance with the results in an SPI paper titled Fast, Robust, Non-Sequential Optical Ray Tracing with Implicit Algebraic Surfaces. This was written in September 3rd of 2015 and presented at an SPI meeting. The system under evaluation is called a Woodhorn's beam dumper light trap, which suppresses stray light through multiple interactions. The fact that it uses multiple interactions makes it an ideal example to test parallel processing inside of ASAP. From the original paper, ASAP 2005 was tested, and the ray trace took about 19.2 seconds. Two internal codes that the author of the paper had created, which are private specialized codes almost exclusively geared toward optimized ray tracing, showed the same simulations at approximately 13.2 seconds and 1.45 seconds on 12 cores. However, it's important to note that they do not have the advanced simulation capabilities of ASAP. Here are the results. As you can see, the speed basically scales with cores and remote. In the initial ray trace, which started off at about 20 seconds, as you add another core, it cuts that just about in half. And then as you add each core, it basically cuts in half the previous amount of time. You do not want to exceed n-2 physical cores or your performance will degrade. What happens here is that ASAP begins doubling up on existing cores and you're effectively running multiple copies of ASAP on the same core. Speed scales with cores and remotes. The host machine, it's important to remember, requires one core and one core for ASAP, but the computational kernel only requires a single core on any remote machine. ASAP running on a single computer can use as many single physical cores that are available. And single ASAP licenses will now include 5 remotes that can access as many single physical cores that are available on that machine. So previous licenses were for 5 remotes, so customers can enjoy a potentially large increase in computing power. Let's now look at a couple of parallel processing examples that illustrate the power of ASAP NextGen's parallel processing. You can manually set the number of physical cores for your simulation, or you can have ASAP automatically allocate the number of cores through the Preferences panel under General Preferences. Just remember that you should not allocate more than n-2 cores for your simulation. The operating system and ASAP both need their individual physical cores. ASAP NextGen's parallel processing is fast, particularly for ray tracing. However, the total analysis time depends not only on ray tracing, but also on the other types of simulations you are performing. In terms of ray tracing, we normally see about a 2x improvement in ray tracing speed as you double the number of cores. When you account for other nominal processing, such as plots, radiometry, and photometric calculations, that speed improvement is on the order of about 1.6x. Even these speed improvements will reach a limit on an individual machine because the computational kernel is operating faster than what the operating system can keep up with during the simulation. We can examine NextGen's parallel processing by looking at 2 sample files. I'll switch over to ASAP in order to do this. The first, source polychromatic 03.inr, is part of ASAP's extensive examples library under the Examples tab in the Workspace area. Click on the Examples tab and expand the Files by Name item and scroll down until you find the file called source polychromatic 03.inr, which is right there. This is a file that sets up a ray set for a multi-die LED and computes photometric and colorimetric calculations of the initial ray set. I'm not going to run this file because of time constraints, but rather show the results for a 1 and 2 core simulation. If you have a copy of NextGen, you can experiment with the file yourself. These are the types of simulation results computed in the example file. For example, there's a calculation of the luminous intensity, the colorimetric, both X chromaticity and Y chromaticity coordinates of that calculation, and then similar calculations done. This first intensity calculation was done in an angle space, and the second intensity calculation was done in direction cosine space. There are similar calculations for the chromaticity coordinates in those particular spaces as well. This is actually what the LED die set looks like. I mean, there are 5 individual dies which are part of this set, and this is a calculation of the luminance pattern of that, and then a corresponding calculation of the colorimetric coordinates of X and Y for that particular source. In particular in the file, note at the bottom of the file the $tick commands before and after the simulation macro commands. The $tick command computes the overall time since the last $tick command, and it therefore gives an indication of the total elapsed simulation time. As you can see down here, the total elapsed simulation time for 2 cores was on the order of 88.91 seconds. If we switch back into the presentation and go to the next slide, we can see that for 1 physics core, the total amount of time for the simulation was on the order of 2.5 minutes. These simulations were done using a 2.3 gigahertz laptop running a 64-bit version of Windows 7 using, of course, in this case, 1 core. This laptop has 4 physical cores, so 1 core is reserved for the OS and 1 for ASAP. The 2 remaining cores, of course, are available for the parallel processing. You can also monitor core usage through your task manager if you so choose. In this case, in the 1 core case, we see 1 core which is running. And now in the 2 core case, you can see that there are 2 physical cores which are running. But let's remember, this is an example of source creation and verification. Let's now look at an example of ray tracing and simulation, but this time let's perform the calculation on a desktop with more than 2 physical cores for the simulation. This next example is an example of an LED headlight designed for left-handed vehicles. So let me switch over to that special computer in order to do these simulations. As I mentioned, this is an example of an LED headlight designed for left-handed vehicles, and we have a picture of that here. Let me move around the 3D viewer and zoom in on the extents of the reflector so that you can see this in a little bit more detail. And then I will put this into a transparent mode as well, just so you can see what's in here. Let me hide the rays for the moment so you can just see what this looks like. So there is the LED down here at the bottom, which is actually a Luxeon Athlon 1x5 LED chip set. It is sitting inside of a basically an elliptical reflector, and then there is a shield out in front of this reflector, which you can see there, and then a lens in front of that. And if I come back into my ASAP and zoom extents on everything and add the rays back in again, you can see that it is propagating light out to a screen which is 25 meters away. Now, this is a left-handed vehicle. These would be vehicles found in places like the United Kingdom and Japan, where in the US we like to say that they drive on the wrong side of the road. Actually, they're driving on the left-hand side of the road, and that's why this is called a left-handed headlight system. In this particular example, we traced about 28 million rays, so from that perspective it is very similar to the previous example. And I ran this already on 2 cores, so you can see what the preferences were set to here. And it took about 2.21 minutes to actually do the full simulation. But let me scan up into the output window here and take a look at the actual ray trace which was performed. And we can get some idea of how long it took to do the actual ray trace. So to trace about 4 million rays, it took about 11.33 seconds. And this is again on 2 cores, and then it took about 2.21 minutes to do the entire analysis. And that included doing this ray trace, opening up the 3D viewer file, and then calculating the photometric values on the screen, as well as the colorimetric coordinates. This is a CIE calculation of that plot. And then this is what the visual appearance would look like. So now, let's go ahead. This is what we have for 2 core. Let's go ahead and clean these and delete these particular simulation results. And I'll come up to preferences here, and I will set this now up to 4 cores. And let's see how long it takes actually to do this particular simulation. So I will restart ASAP, and we're going to do this one in real time because it goes pretty quickly. So I'm going to go ahead and press the run button, and we're going to let this calculate and do its simulation, and we'll look how long it takes for the results. Again, this is a simulation with about 28 million rays. It was based upon a Luxion 1x5 Athlon chip. We're using actual data from the manufacturer in order to simulate the chip in order to get simulation. You can see right here, it's taken now about 12 seconds. It's close to 12 seconds before for 4 million rays, but we've doubled the number of cores. So we've traced twice as many rays in the same amount of time as we did previously. And so I'll let this continue on and finish out, and we'll see how much time it takes to do the entire simulation. So on 4 cores, it took roughly 84 seconds or so to do the entire simulation. Very good. Let's go ahead and now run this, doubling the number of cores again, and let's see what kind of simulation results that we get. Go to our Preferences tab. We'll take this up to 8 physical cores. Apply those changes, restart ASAP, and then we will run this simulation again, and let's see what kind of results that we get. Okay, to do the entire simulation, it was on the order of 47 seconds, and we might have been fooled a little bit. It seemed to be taking a long time to do that ray trace, but let's come up here and see what's going on with the ray trace. Actually not. It took about 25 seconds to trace nearly 30 million rays using 8 cores in ASAP NextGen. So that is for me, that's really quite impressive. When I first started out using ASAP many years ago, tracing rays on a DEC VAX, it took about 20 minutes to trace, I'd say maybe 300 rays. We are now tracing nearly 30 million rays and performing simulations in less than a minute.